Hello, so in this video I'm going to take you through the atom economy calculations for the higher chemistry course. This falls within Unit 3 Chemistry and Society, and it kind of falls in line with the getting the most from reactants subtopic. So the purpose of this video is to teach you how to state the definition of atom economy and then show you how to calculate the atom economy for a desired product in a given chemical reaction. So atom economy is a percentage, and it's the percentage of reactant atoms that end up in your desired product. So if we look at this reaction here, where we're burning magnesium to make magnesium oxide, the atom economy for this reaction would be 100% because all of the atoms in the reactants are ending up in our desired product. And that's because there only is one product. So for any chemical reaction or chemical process that only produces one product, the atom economy will be 100% because 100% of the reacting atoms are ending up in the product. So if we look at a different reaction where we're making more than one thing, usually most reactions will make two products. One of the products you tend not to really need, the other one is the one that you do want. The product that you want, and that's the whole reason you're doing the reaction, is known as the desired product. So in this particular reaction here, the desired product is solid copper. So you can identify that by the fact that the question says calculate the atom economy for the production of copper in the below reaction. So it will tell you what it's wanting the atom economy with respect to. In order to calculate the atom economy of a reaction, we use this equation down here, which you'll find on the contents page of the data booklet, or the equation page in the data booklet. So it's the percentage atom economy is equivalent to the mass of desired product, or products if your reaction is making more than one thing that you want, divided by the total mass of all the reactants times by 100. So if we actually do this calculation for this particular reaction, so we need to work out the gram formula masses of each of the reactants and then our desired product. So we need these two and this one, the copper. We don't really need to worry about the magnesium sulfate because that's what we would class as a byproduct, something that's produced that we're not actually interested in. So the gram formula mass of magnesium is 24.3 grams. So that's just the relative atomic mass. For copper sulfate, we have 1 copper, 1 sulfur, and 4 oxygens. So if we add that up, 63.5 plus sulfur, which is 32.1, plus 4 times 16 for the 4 oxygens, that's 159.6 grams. And then the copper solid, 1 mole of copper is 63.5 grams. So then what we do is put these masses into our atom economy equation. So percent atom economy. So the mass of desired products goes on the top. So that's copper. We've only got 1 mole of copper, so that's just going to be 63.5 grams. The mass, total mass of the reactants, so we've got 1 mole of magnesium, which is 24.3, plus 1 mole of copper sulfate, which is 159.6. And then times by 100. So then if we put that into the calculator, 63.5 divided by 24.3 plus 159.6 times by 100, that gives us 34.53% to 2 decimal places. Okay, you could round that up to 35%, you could round it to 34.5%, it's fine either way. So that's one example. we look at this example here, so this time we're looking for the atom economy for the production of water. So water is our desired product, and then we always need the total mass of the reactants. So 1 mole of methane will be 16 grams, 12 plus 4 for the hydrogens. Oxygen, the gram formula mass of oxygen, because it's diatomic, will be 32 grams, 2 times 16. So just bear in mind, these are the GFMs. I've not taken into account that there's 2 moles of oxygen yet. And then water's gram formula mass is 18 grams, because that's 2 for the hydrogens plus 1 for the oxygen. Again, I've not taken into account that there's 2 moles of it yet. So our percent atom economy. So the total mass, or the mass of desired products, if we were only making 1 mole of water, it would be 18, but we're making 2 moles, so that'd be 2 times 18. Then for the total mass of reactants, we've got 1 mole of methane, which is 16 grams, plus 2 moles of oxygen, so that would be 2 times 32 grams, times by 100. So if we multiply out the top, well, you can just put it all in your calculator at once, really. So 2 times 18 divided by 16 plus 2 times 32. If you're putting it into your calculator all in one go, just make sure you're appropriately using brackets. Times by 100 ends up as 45% atom economy. So that means 45% of the atoms you're reacting together end up in the water. So example 3, calculate the atom economy for the production of silver. So, and then we always need our reactants. So the gram formula mass of copper is 63.5 grams. Silver nitrate is 107.9 plus nitrogen, which is 14 plus 3 times 16 for the oxygens. So that's 169.9 grams. And then 1 mole of silver on its own is 107.9. Sorry, took me a while to see it there. So then we've got our percentage atom economy equation. So mass of desired products, we've got 2 moles of silver, so that's going to be 2 times 107.9. And then that's going to be divided by 1 mole of copper, which is 63.5, plus 2 moles of silver nitrate, because there's a 2 in front of there. So 2 times 169.9 times by 100. So we type all that into the calculator. Gives us times by 100, 53.5%. Then example 4, this time given the gram formula masses, so sometimes you'll be given the mass of 1 mole or the gram formula mass in the question, which means you don't have to work it out yourself using the data booklet, so it kind of saves you a bit of time when it gives you them. So this time we're calculating the atom economy for the production of ethyl ethanoate, so that's this one here, and then obviously we always need the reactants. There's no numbers in front of these words, which means it's just all 1 mole, so everything's 1 mole, 1 mole, 1 mole, 1 mole. So our percentage atom economy, the mass of desired products, so it's 1 mole of ethyl ethanoate, so that'd be 88 grams, divided by total mass of reactants, so that's 46 grams for the 1 mole of ethanol, plus 60 grams for the 1 mole of ethanoic acid, times by 100. So 88 divided by 46 plus 60 times by 100 gives you 83%. Okay, and then the last example is one that basically tests your knowledge on atom economy. So you could use the equation and calculate it if you wanted, but it would be worth less marks in an exam, and it also uses the command word state rather than calculate. So if you're asked to state the atom economy, you should be able to work it out just from looking at the reaction equation. So the atom economy for this reaction is, is 100%, because you're only making one thing. So all of your reactants are going towards making that water. Okay, so if your reaction is only making one product, your atom economy will always be 100%. And if the question tells you to state the atom economy, it's not expecting you to use a calculation. It will only be worth 1 mark, and it should be fairly obvious what the atom economy is, i.e. it's usually 100%. If it did say it on the first slide, but if the atom economy for a reaction is really low, it's seen to be a fairly wasteful chemical process. So if it was necessary to carry out that chemical process, then what you would probably want to do is try and recycle some of your byproducts, i.e. the products that you're making but don't really need from that reaction, or try and make the process more economical in terms of the atom economy. Try and find a reaction that's got a higher atom economy that makes the same thing. But usually the easiest way to make it more economical would be recycling some of the byproducts or either selling it on for profit. So hopefully now you can state the definition of atom economy. You can state that reaction has an atom economy of 100% if only one product is produced, and that you can then also use the atom economy equation to calculate the atom economy for a given reaction. Thank you.